Hey everyone, welcome to the final video in our indices and surd series. Now, because we've covered a lot of different indices and our different index laws, all the way from multiplication of same bases, division, negative indices, and powers of powers, as well as fractional indices, really from the year 10 course, at least in this 5.31 that I'm working through from the Australian syllabus, the only thing left that we haven't done in indices yet is starting to think about solving what we call exponential equations. Now, what we mean by these is these are any equations dealing with some kind of power or some kind of exponent. Okay, so some of you may be thinking, well, we've seen similar things like this. What about when we solved, for example, like quadratic equations? Something like this. Well, we used all the techniques we had started to build up on to think about how we could solve something like this. But the difference here now is that our unknown is the actual exponent. Our unknown is in the power. And what we're going to be doing in this video is working through these abstract sort of questions by considering all of the building blocks from indices that we've learnt so far. So if any of these index laws or anything I'm going through in this video is unfamiliar to you, please consider looking at some previous videos if you need to, for example, brush up on negative indices or fractional indices or anything of that sort. Now, what we're doing when we solve exponential equations is we are solving equations of this particular form. And the particular examples we're going to be doing, we're always going to have some kind of base, some number, and a constant on the other side, and our exponent, as we talked about before. Now, our base number, a, this number, at least with the equations we're going to be solving, is going to be greater than 0, and it is not going to be equal to 1. Now, why is this the case? Because when we take 1 to any power, the answer is always going to be 1. So this is something we call like the trivial solution here. So it's solving these is almost redundant because anytime we have 1 to the power of anything, the answer is always going to be 1. We're moving towards some more challenging questions with different types of bases here. Now let's have a look at this just little example I've written down here. This 3 to the power of x equals 3 to the power of y. You may notice both of these numbers have the exact same base. I have a base of 3, I have a base of 3. So whatever powers I input, these two expressions here are going to grow together, right? So the only way my left-hand side is going to be equal to my right-hand side is if my exponents were equal as well. So in this case, x and y are the same. Now, what led us to this actual conclusion? Well, what told us that was in order to even work through something like this, we need to have both of these terms on the left-hand side and the right-hand side of my equation as having the same base. Because if they have the same base, we can say that the exponents, the powers, are equal as well. Now, it might be a bit of a weird thing to wrap your head around. So let's just jump straight into some examples and I'll show you what I mean by this, because this is going to be a really useful strategy for solving these types of equations. Now, I have this particular equation here. 2 to the power of something equals to 16. Now, there's no way we can really do this unless you've kind of memorized all your different powers and you can jump to figure out what 2 to the power of something higher than 2 or 3 is in your head. But what we're going to do is we are going to consider trying to make this number here have the same base as my term on the left. So a base of 2. So this may need you to do a little bit of trial and error maybe into your calculator, trying out different powers of 2. But if I just do this here on the right hand side, 2 to the power of 1 equals to 2. 2 to the power of 2 equals to 4. 2 to the power of 3 equals to 8. And you can hopefully see here, as we go down, our number is always doubling. So if this were to keep doubling, if I go up one more power, 2 to the power of 4, that's going to be 16. Because once again, my numbers will continue doubling. Now, what that means, why that's useful, is that now we can write this 16 as a number with an exponent, with the same base number as this guy on the left-hand side. So what we're going to do now, the left-hand side is going to stay the same, but instead of 16, I can write 2 to the power of 4. So once the bases are equal, well, we can just read off, well, 2 to the power of something has to be equal to 2 to the power of 4. So therefore that something x has to be the same as this power on the right hand side. And the reason this works is because of this equality idea. With any equation, the left hand side is equal to the right hand side. So the only way my thing on the left is going to be equal to my thing on the right is if the powers are equal as well. So that allows us to make the conclusion that our power on the left hand side must be the same one as the power on the right hand side. Let's try another one here. Maybe a slightly weirder one. Now once again, in order to solve these types of equations, I want to get both this and this expressed with the same base. So because I have an exponent on the left hand side, my base is going to be 3. So I want to try to write this guy with a base of 3. Now you may notice this is a fraction. So when we have a fraction and we have this kind of bigger number on the denominator, this implies we're working in our negative indices range. So let's just try a couple of different, putting in a couple of different values and seeing how we can write this 1 over 9 in terms of my indices of base 3. Now 3 to the power of 1 is 3. 3 to the power of 0, well, any number to the power of 0 always gives us 1. 3 to the power of negative 1, that's going to be 1 over 3 to the power of 1, or just 1 over 3. And remember, when we look at negative indices, instead of our numbers doubling, our numbers are going to divide. So here, to get from here to here, I divided by 3. Here to here, I divided by 3. So therefore my next step, my next negative indice is going to be 1 over 3 squared, or 1 over 9. This is just a revision of what we were doing with negative indices. So please, if this is unfamiliar, have a little bit of revision of this before we move on to these tricky examples. But because we have a fraction with some denominator, we can write 1 over 9 as 1 over 3 squared. Now I have the same bases here. But now 1 over 3 squared, this is a fraction at the moment. I want to write this just as an integer, a whole number, to some exponent, to some power. And the way we're going to do that is I'm going to write this 1 over 3 squared as just 3 to the power of -2. And that just shows this relationship on the right hand side here. This is just a revision using what we know from negative indices to approach a more abstract question. So now that we have the same bases, I have a base of 3, I have a base of 3. Since these are equal, the only way that the left-hand side is going to be equal to the right-hand side is if the exponents, the powers, are equal as well. So therefore, I can make the conclusion and say the only solution to this equation is going to be when x equals to -2. And if you want, you can check this. You can substitute -2 into here, put it on your calculator, in your calculator I should say, and then you'll end up with 1 over 9 as your answer. Okay, let's keep going. We're looking at a slightly more tricky example here. We're going to take quite a few steps to approach something like this. Now, with this particular question, there is no way so far that I can relate these in the same way I've done before. Because if I take 25 to some power greater than 1, because 25 to the power of 1 is just 25, and then taking 25 to the power of 2, that's going to give us a much bigger number than 125, this number on the right hand side. So we want to find another way to relate these numbers. Now, 25, I'm going to look at that number and say, wait, that looks curious. If I look at 25, 25 is a perfect square. So I can get 25 using a base of 5. I know that 5 to the power of 1 is just 5, and 5 to the power of 2, or 5 squared, is 25. Okay, so if I write these in, I can see that, okay, getting from the first to the next one, I'm multiplying by 5. So 5 cubed, 5 to the power of 3, that's just going to be 25 times another 5, because 5 cubed is just 5 times 5 times 5. And that gives me now 125 here. So our relationship between the two terms are a little more abstract than before. But I can still make a link to 25 and 125 through this idea of writing both of these expressed with the same common base of 5. So instead of writing 25, I'm going to write this as 5 squared all to the power of x. Because this is just some number to the power of x, so I'm rewriting that as just another number with the same number, just with a different base. And my 125, I'm going to write that as 5 to the power of 3. Okay, well, when we looked at indices before, when we considered index laws and things like that, we said that when we have some number with a power, and we took the power of a power, that gives the effect of these two multiplying by one another. When we take a power of a power, the two powers multiply. So I'm going to get 5 to the power of 2x equals 5 cubed. And now we have written all of these, well, both of these two terms on the left and right side of my equation, with a common base of 5. And since we have an equal sign, we're trying to find a value of x that makes the left-hand side and the right-hand side equal. Now, once again, because we have the same base, that means the only way for these to be equal is if the powers are equal. So this allows us to say, well, okay then, my power of 2x has to be equal to 3. And this just becomes a secondary, smaller equation that we can solve. So 2 times some number gives me 3. Now, because this is a multiplication, I can just do the opposite operation to give the effect of, well, 2 divided by 2 just gives me 1 in front of x, which just gives me x on its own. So that means that therefore my x is going to be equal to 3 over 2. This one is a little bit trickier, but we can also just check, like we do with all equations, we can check by substituting. So I'm going to substitute x to the power of, x equals 3 over 2 into my equation here. So I have 25 to the power of 3 over 2. Well, I can write that, since we have a fractional indice, I can write this thing as, 25 to the power of a half, all cubed, because I'm pretty much just splitting up my 3 over 2 into just 1/2 multiplied by 3. I'm making a product with these two numbers, but I'm just going in the opposite direction. Now, 25 to the power of a half, that's like saying the square root of 25. We learned this from fractional indices, all cubed. So the square root of 25 is going to be 5, and we're cubing that. 5 cubed gives me 125. So I get to where I need to go still. Now, that is how we can work through a question like this. Now, this one was a little bit harder because there was no apparent initial relationship between these two bases here. But we can get them to the same base using a number that we can make into each of these via powers and via these exponents. All right, one more question right at the end, and this is going to be a far trickier one in terms of there's just going to be more steps, but through this same kind of mathematical manipulation, we can do this in the same type of way. Now, 3 and 27 have no apparent initial relationship. But if we consider some of our powers of 3, 3 to the power of 1 gives me 3, 3 squared gives me 9, and 3 to the power of 3, or 3 times 3 times 3, is going to give me 27. So going down each of these, I'm multiplying by 3 every single time. So this now gives us a relationship between 3 and 27. I can write 27 with a base of 3 here. So I'm going to take a moment to do that. So this gives me 3 to the power of 2x minus 1. That stays the same. Now 27, instead of writing this as 27 to the power of x, I'm going to write this as 3 to the power of 3 to the power of x. And now, once again, I have a product of a product here, a power of a power. So these two guys, these two powers, whenever I have this, they are going to multiply together. This is just a review of the index laws we've been working with up until now. So I have 3 to the 2x minus 1 equals to 3 to the power of 3x. And now I have these as two expressions with the same base number of 3, left and right. Now, because we have the same base number, the only way these two can be equal is if my powers are equal, because I have the same base number. Therefore, we can say that 2x minus 1 is going to be equal to 3x. And solving this equation now, I want to group all the x's together. So what I'll do is from the left, I'll subtract 2x. That will give me just 0 here. And what I do to one side, I want to do to the other. So on the left-hand side, I have 0 minus 1, which just gives me minus 1. And on the right-hand side, I have just 3x minus 2x gives me one lot of x, or just x. So now we have a solution to the equation. And like always, we can check this by substituting back in. Okay, so what we're going to do, we're going to put x equals negative 1 into both of my x values in the power. So let's just have a look at that, see how that's going to work. So I have 3 to the power of 2, and instead of x here, I'm going to put negative 1 minus 1 equals 27 to the power of minus 1. Okay, so on the left, I have 2 times minus 1 gives me minus 2. So 3 to the power of minus 2 minus 1 equals to, well, 27 to the power of negative 1, I can write as 1 over 27 using what I know about negative indices and what this does to my number. And here I get 3 to the power of negative 2 minus 1. That gives me 3 to the power of negative 3. And 3 to the power of negative 3, I can write that as 1 over 3 to the power of 3. With these negative indices, I can always take the reciprocal and my power will become positive on the denominator. And I have my thing on the right that doesn't change. And I know from before that 3 cubed equals to 27. So my left-hand side equals my right-hand side. So x equals minus 1 is a solution to the equation. Now, with all of these we've been doing so far, you may have noticed there is always one solution. But this is how we can approach these abstract exponential equations questions using a bit of manipulation of our terms in order to first get the same base, and then using that same base to state that then the powers must be equal. And then it just becomes a matter of just solving for x, solving for your particular power, the value that's going to make, value of x that makes those two powers equal. But that brings us to the end of this topic and, well, surds and indices in general. Thank you so much for joining me, and I will see you in the next one.